Hello everyone. In this video, we are going to discuss the entropy for reversible process. First of all, we define the entropy and then we will discuss the entropy for reversible process. First of all, consider a reversible process. For example, we have a PV diagram here. On y-axis, we draw the pressure. On x-axis, we draw the volume. And for example, a system which has a state here, state A, and here is a state B. And if the system goes from A to B in this process, A to B, and then finally comes at A. It is a cyclic process, and for example, it is a reversible cyclic process. Then, according to the Clausius theorem we discussed in last video, the Clausius theorem tells us that the integral on a closed path for a cyclic process, for any cyclic process, the dq over capital T is less than or equal to 0. And now for just reversible cyclic process, this integral, closed integral dq over capital T is just equal to 0. Now this integral we are considering for reversible process. For reversible process, we are considering Clausius theorem. The closed integral dq over capital T is equal to 0. If we break this integral, as the cyclic process A goes from A to B and then B to A, and we can break this integral from A to B in dq over capital T, dq reversible, plus integral from B to A and dq over capital T and reversible is equal to 0. As dq over capital T is an exact differential because it does not depend upon the path followed, it is called exact differential. And it is also the definition of entropy. It is called ds. The definition of entropy ds is dq reversible over capital T. Now if we integrate this, or we move this integral b to a dq to the other side of the equation, we will get the integral from a to b dq reversible over capital T is equal to integral minus integral b to a and dq reversible over capital T. If we exchange the limits from on right side of the equation, b to a to b, then the minus sign will be absorbed and it will written as a to b dq reversible over capital T. It is a definition of our entropy, and which will become the SA SB minus SA, the change in entropy. This is the definition of change in entropy for a process, for reversible process. Because this is a exact differential, dq reversible over capital T is exact differential, it means that it only depends upon its initial and final states. That's why the ds is also called state function. If it is a state function, then for cyclic process, reversible cyclic process, if we move from a process goes like A to B and then comes to its initial position A, then its change in entropy for cyclic process, reversible cyclic process, will become 0. The change in entropy for reversible cyclic process its change in entropy delta S is equal to, because it is the state system goes from A to B and then B to A, its initial and final position is same, and ds is a state function, the entropy is a state function, it only depends upon the initial and final state. That's why its change in entropy is 0. Now consider the example of some reversible process. Let's we have a system which is thermally in contact with surrounding, and let's the temperature of system is T1 and the temperature of the surrounding is T2, and we do some compression of this system, and due to the compression the heat will goes from the system to the surrounding. Let's say it is heat, the dq, reversible. Then the change in entropy, here the change in entropy for the system is integral dq over capital T1, and it is negative because the heat is leaving from the system. And if we write the change in entropy for the surrounding, it will become integral positive dq over capital T2, because the heat is entering to the surrounding, the heat entering is taken as positive and heat leaving is taken as negative. And if we calculate the change in entropy for the universe, the change in entropy for universe is equal to the change in entropy for the system plus change in entropy for surrounding. Now the change in entropy for the universe, our total change in entropy is equal to the change in entropy of the system is minus dq over capital T1 and plus dq over capital T2. As this process is reversible, and if we are going to the reversible process, then the temperature of system and surrounding should be the same. For quasi-static process, the temperature T1 and T2 should be the same. For reversible process, the temperature T1 should be equal to T2. This is also called quasi-static process. Then the change in entropy of the universe is the change in entropy of the system and change in entropy of the surrounding will be cancelled out because the T1 and T2 is same. Then the both integral will give the same answer, and we will get the change in entropy for the universe is equal to 0 for reversible process. If we consider the reversible adiabatic process, reversible adiabatic process, as we know that the dq is equal to 0 for adiabatic process, and for reversible process the change in entropy is by definition is from A to B and dq over capital T. As dq is equal to 0, then the change in entropy is also 0. The change in entropy for the adiabatic process, reversible adiabatic process, is 0. It is also called isentropic process.